Today's lesson is on radicals and rational exponents. This is the third lesson of our review section. The essential question for this section is, what are the basics of radical expressions and how do you use rational exponents? So we start off talking about square roots. As you are all aware, if you take 5 and you square it or multiply it by itself, you're going to get 25. And the reverse operation of squaring a number is finding the square root of the number. In general, what we might say is that if b squared is equal to a, then b is a square root of a. We have several rules regarding how we use square roots and radical expressions. Now you may initially think that simplifying the expressions of the form the square root of a squared is simply equal to a. However, this is not necessarily true. For example, if we have 25, minus 5 times minus 5 is equal to 25, as well as positive 5 times positive 5 is equal to 25. So we do have to come up with a rule for simplifying expressions of the form the square root of a squared. And that rule is that the square root of a squared is equal to the absolute value of a. Or in words, the principal square root of a squared is the absolute value of a. The next rule we have is the product rule for square roots. And this states that the square root of the product AB is simply equal to the square root of A times the square root of B. Similarly, you can go the other way and say the square root of A times the square root of B is equal to the square root of the product of AB. As an example, let's say we had the square root of 500. Well, that is simply equal to the square root of 100 times the square root of 5. Well, the square root of 100 is 10. So our simplified answer is the square root of 500 is equal to 10 times the square root of 5. Next, we have the quotient rule for square roots. So if we have the square root of a over b, that's simply equal to the square root of a over the square root of b. And similarly, if I have the square root of a over the square root of b, that's equal to the square root of a over b. For example, let's assume that we had the square root of 100 over 9. This is simply equal to the square root of 100 over the square root of 9, or simplified is 10 over 3. The next rule we want to talk about is adding and subtracting square roots. Now, 2 or more square roots can be combined using the distributive property, provided they have the same radicand. What in the world does that mean? Basically, they have to have the same value underneath the radical sign. For example, 7 times the square root of 2 plus 5 times the square root of 2 is equal to 7 plus 5, which is 12 times the square root of 2. Similarly, 2 times the square root of 5x minus 7 times the square root of 5x is equal to minus 5 times the square root of 5x. Occasionally you're going to find situations where combining radicals at first appears to be impossible, but once you simplify one of the radicals, then it becomes possible. For example, let's say we had 7 times the square root of 3 plus the square root of 12. Initially, you'd look at that and you'd say, well, I can't combine the square root of 3 and the square root of 12. However, if you look closely, the square root of 12 is actually the square root of 4 times the square root of 3. So the square root of 4 is simply 2, which you can see right here. So now we've got 7 times the square root of 3 plus 2 times the square root of 3, which comes out equaling 9 times the square root of 3. So originally what we thought we could not combine, since we had the square root of 3 and the square root of 12, by simplifying the square root of 12, we can combine these two and come up with a simplified answer. The next rule we're going to talk about is rationalizing denominators. Whenever we have square roots or radicals of any form, it is considered non-standard if the radical is in the denominator. So basically we have to take and rewrite the radical expression as an equivalent expression in which the denominator no longer contains any radicals. And this process is called rationalizing the denominator. For example, let's say we have 1 over the square root of 3. We've got a square root of 3 in the denominator, so we want to get rid of that. Well, if I multiply the square root of 3 by the square root of 3, that will give me the square root of 9, or 3, and get rid of the radical. But remember, whatever you do to the denominator of a fraction, you must do to the numerator. So if I simply multiply by the square root of 3 over the square root of 3, in effect I'm only multiplying by 1, so I'm not changing the value of my fraction at all. And the result that I get is the square root of 3 over the square root of 9, or simply the square root of 3 over 3. So this is how we rationalize denominators. Now what do I do if I have an example like this? Let's say I have 7 over 5 plus the square root of 3. I can't simply multiply by the square root of 3 because that'll get rid of the square root of 3, but now I have 5 times the square root of 3 as well. So how do I handle this? I handle this by multiplying something called the conjugate, which is the same term as what is in the denominator. The only difference is the sign has changed. So if I multiply, again, I'm multiplying by 1, which is 5 minus the square root of 3 over 5 minus the square root of 3. The numerator simply becomes 5 minus the square root of 3 times 7, or 35 minus 7 times the square root of 3. The denominator, if we FOIL this, we'll find that the first term is 5 times 5, or 25. The middle two terms are going to cancel. In one case, you're going to get minus 5 times the square root of 3. In the other case, you're going to get positive 5 times the square root of 3. So those will cancel. And what you're left with is the last term, which is a positive times a negative, or minus the square root of 3 times the square root of 3, which comes out to be 3. And our final answer simply is 35 minus 7 square roots of 3 over 22. All right, one last thing we're going to talk about, and that is rational exponents. Now this is where your exponent is a rational number, or put simply, is a fraction. So say, for example, we have a to the m over n, where m over n is a rational number. Now this can be written two different ways. First, we may simply write it as the nth root of a raised to the m power. Or if you prefer, we could say a to the m power, and we're going to take the nth root of that. So we can either raise it to the power and take the root first, or take the root first and then raise the answer to the power. Either way, both are acceptable. So let's look at an example where we might use this. So let's say we have 27 raised to the 2/3 power. How would we handle this? So first we would take the third root of 27. So that is simply equal to 3, because 3 times 3 is 9 times 3 is 27. And then we would square, so our final answer would simply be 9.